thank the organizer of CanSec 2021 for giving me the opportunity to give a presentation on detection of message injection attacks into the CAN bus using similarities of success message sequence graph. Also, I would like to thank everyone that listening to my talk today. So let's begin. So modern vehicles are equipped with a number of ECUs that can range from 20 to 70 ECUs, and it can reach up to 100, 110 ECUs, depending on the car models and the car manufacturers. So as we can see on the right, we have a vehicle that depict how ECUs with actuators and sensors that are wired together using using the CAN bus. So inside those ECUs, we have a software up to 100 megabit binary of code that controls the car functionality from speed brake to airbag deployment, door controls, light controls, etc. Also, those ECUs, like I said, they exchange messages through the CAN bus, and the CAN bus enables this communication within the vehicle and with external entities such as vehicle to vehicle communication and vehicle to infrastructure communication like the traffic lights and GPS, Bluetooth, and onboard Wi-Fi. So what is the CAN bus? So the CAN bus is a protocol that was developed by Robert Bush in 1983. It's a low-cost, lightweight network that's enabled communication within the ECUs. So as you can see at the bottom, we have without the CAN, the wiring get complex and complicated, and it will add weight into the vehicle. But within the CAN bus, it's simple and it does not require a lot of wiring. Also, it will allow for more ECUs to be added into into the CAN bus for driver comfort and road safety. So the CAN bus consists of high and low signals, and it has four frames. We have the one of the frames is the data frame used for exchanging messages, and there's also the error frames that used for detecting of error, and there is the overload frame which you use for delaying of messages between the ECUs, and then we have the remote frame which is used for requesting of data from an ECU. So the data frame, it consists of the arbitration of the identifier field, which it consists of 11 bits, but it could be up to, but in extended CAN it's 29 bits identifier field followed by the control followed by the data field. And at the bottom we have a CAN data that was extracted from a vehicle using the CAN 0 interface. So on the left we have the timestamp in Unix, followed by the CAN interface CAN 0, followed by the ID, and then followed by the data. So, so the CAN bus was designed with no security being implemented to it. It's robust and it had error detection mechanism for if a frame that's collided with another frame, it could detect that. But there's no authentication built into it or authorization. So when data gets sent between the ECUs, the ECU doesn't know who sent the data. So there's only the message identifier field that will identify who should get the frame, who should get the data. And also there's no encryption or anomalous detection mechanism. So any ECUs with a higher priority can flood the bus with messages. So the message gets sent based on the priority on the on the de- on the identifier field. So an attacker can connect to the bus and can flood it with low priority. And then also the informatics system, that the more ECUs get added into it, like apps and onboard Wi-Fi and Bluetooth and a USB connection. That will increase the attack vector, the attack surface for hackers. And the canvas can be accessible remotely or locally. So locally through the onboard diagnostic port, which is located under the steering wheel. It's usually used by mechanic for diagnostics. So if you get a check engine, you take your car to the mechanic, so they plug in a little device under the steering wheel to figure out what's wrong with the vehicle. Remotely, that could be through onboard Wi-Fi or through the Bluetooth. In 2019, there's 120 reported CSV related to security issues on the campus and on the ECUs. So on the chart here, we can see that the number of cyber reported incidents it keep increasing from year to year, and from 2018 to 2019, the number doubles, and in 2000 from 2016 to 2014, the number increased by 94%. Also, most of the reported security issues on the account protocol is related to car theft or break-in, 31%, and then 27% controlling the car system. On the left, on the right, we have the top 2020 reported incidents on the CAN bus. So first, we have the 19 vulnerabilities were reported for Mercedes-Benz E-Class, which allow hackers to control the vehicle remotely, including opening doors and starting the engine. Also, there was reported vulnerabilities for Tesla that allow hackers to control connected vehicle Tesla entire connected vehicle fleet by exploiting vulnerability in the ECUs. Also, there is more than 300 vulnerabilities were reported over 40 ECUs developed by Tier 1 companies. So as a result, the research community proposed a security solution for securing the CAN bus. So Faraday proposed a CAN track for encryption of ECU's messages. So each message get encrypted with a key and then it gets sent. Also, Hirsch proposed the use of a secret key. So, so in order for messages, so there's, as I said, there's CAN high and CAN low. So to switch from CAN high to CAN low, you need to use a secret key. And Taylor proposed an IDS based on message frequency using Hammond distance. And also there's a couple of reported machine learning technique that uses the CAN bus frame features like the control field or either the data field um, to detect anomalies on the system. Other use entropy. They use timing of the messages, so they measure the time of how many how many. So if we select an ID 119, so measure the time how many of the ID appear in a time frame. So there's a limitation to that. So one of the limitation that most of the proposed solution they use synthetic data from a stationary vehicle or from a simulator, which had which will have an effect. So a car being driven on the road versus in a stationary vehicle, the frequency of messages get exchanged on the canvas is different. So say for example, if we have a message of increasing the fuel, should be followed by increase of the RPM and then should be followed by increase in the speed. Also also they require modification of the CAN bus design, which is not feasible because due to the constraint of the ECU used and even the timing. So for example, if you want the car to brake, it need to act fast. So the brake ECU need to act fast. So if we add an encryption layer into it, then it will slow down the communication and we might have a catastrophe or a fatal accident for the drivers. Also the capability or the computing processing power it's limited. So adding encryption, it will slow down and it's not going to be feasible. So the research question that we had: can we detect cyber attacks on vehicles without knowing the IDs of the vehicle ECUs? So Dr. Lutfi bin Usaymin have demonstrated that injunction of messages into the CAN bus. So as you can see here on the left, we have the RPM reading is not changing, and on the right, that's when the injected messages. So the RPM jumped to a maximum, and it can be shown here on this video. So just injecting the RPM messages, it would be changed on the instrument display or the instrument ECU that display the messages. So as a result, the frequency of the messages change, and we hypothesize that if we inject a speeding reading and then capture the behavior of the messages that get exchanged into the CAN bus, we can develop a mechanism for detecting of attack. So as you can see here, that injecting of ID 254 with 0FF, which is equivalent to 25 miles per hour, it will affect the frequency of the messages into the CAN bus. Similarly, for the RPM, injecting the RPM reading 115 FFF, which is equivalent to 120 RPM, 120k RPM. So it will change the frequency. So capturing that, we can use graph to graph those messages, and then using similarity techniques, we can detect how similar how similar at how similar the two vector are, or the two data are. Say for example at time t and then at time t plus 1. So the experimental data set consists of three data sets. It's normal with no injected data of 23,000, and then injected speed data of 88,000, and then three injecting of RPM of 30,000. So like I said, we extract the data and then we graph the message, and then we're using feature extraction to measure the similarity at time t, then at time t plus 1, with t plus I, or t plus I, and I is just the the time. It's 1, 2, 3, or 4. And then we use prediction techniques such as long short-term memory, or using a search hole, or point change detection to determine where if there is an injected of messages or not onto the dataset. So graph are a great way of represent relation between entities, and it's used for fraud detection. So here we used it to graph messages. So on the left we have a time t, and then on the right we have a t plus 1. So as you can see that there is a change between 118 to 344. So we represent IDs as node, and then the connection between the ID and ID as edges, and then we measure how many times we seen that the connection between those two nodes, and then we store that in a vector, and then we use cosine similarities. Cosine measure the angle between two non-zero vector and determine if they point to the same direction. Usually it's used for parallelism, so for detecting if someone copy a paper from another source. Here we used it to determine if the two vector or two data set are similar or not. And then we used Pearson correlation, which measures a linear relation between two vectors. So it's similar to the cosine. So to see that if the two vector at time t and t plus 1 are they different or not. So As a result, we use a cosine similarity and then we graph the distribution of the cosine similarities. And then we use a t-test to determine that if the two distributions are indeed from two different populations. So as you can see on the graph, we have that on red, that's the speed data, and on green, we have the normal data. Also on the right, we have the RPM and the normal data. And the t-test indeed confirmed that injected messages, it will change the frequency. Injecting message into the CAN bus, it will change the frequency of the message exchange into the CAN bus. Also, we did a time plot which is indexed by time. So at time 0, and then here showing 50 or 100, it's increasing. So as you can see that as messages get injected into the CAN bus, the frequency change and is shifted. So first they start together, and then as soon as the injected attacks into the vehicle, the frequency of those messages change. Similarly, for the Pearson correlation, it detected that the two distribution are indeed are different. So this is just a time plot of the two distribution. So as a result, we use a threshold of 0.87. So above that, it's no attack. Under below that, there's an attack. So we had 3.3 and 2.67 false positive, and for the RPM, and then for the speed, it was a little bit higher. Also for the LSTM, we we only missed 3, so it was pretty accurate. So it was 97.3%, and then we use the point change detection. So the idea here is that we have a series of data. As you can see here, we have a series of data that's indexed by time. So we're trying to predict when when that when the data shifted, or we try to predict the change point. Where did that change point happen, or if there is a change point on the data set. So the result was that the change point for the RPM was 66, but it was actually 34. For the cosine similarities, and for the speed, it was 39. It was 391 and 169. Also for the Pearson, it was 54, and but the actual point change happened at 34. So it can be noted here, we measure the sensitivity. So even though it would say that there is a change point of the normal data, but it had a lower sensitivity compared to the sensitivity of the RPM data. So the sensitivity for the normal data was 0.811% compared to the RPM data, which it had a 10% sensitivity for detecting change on the dataset. As a result, we concluded that there is an actual change using the sensitivity of the change point detection. So car hacking is real. There's more than 188 reported security incidents in 2019, and it's scary. Like, it's scary seeing that the number of reported vulnerabilities in ECUs and the campus, it keep increasing. We developed an IDS using message sequence graph for detecting injunction of messages, and we have a detection accuracy of 97.3% with a detection speed of 2.5 millisecond. So the IDS is suitable for real-time detection, and it can be tested on different car controllers. Here's the team. It's me, Mubarak Jed. I'm a PhD student. My advisor, Dr. Lutfi bin Usaimin, assistant teaching professor at Iowa State University. Noor Ahmed is a PhD in computer science in the Air Force Lab, and Dr. Bakar Wahab with the Department of Computer Science at Purdue. Thank you, and I'll be happy to take any question.